Okay, so the problem I have up here, it's an example of a couple of things that we talked about last week. One is dosages based on weight. Then the other is titrations, dealing with adjusting a dose once we've gone through a calculation. And then also dealing with safe dosage. Is this dose safe for this patient? So let's go ahead and take a peek at what's going on here. So we have the doctor's orders are for 400 milligrams of amoxicillin, but we also have to look at the time frame. That is every 6 hours. So that's 400 milligrams every 6 hours. We're dealing with a patient here that is 99 pounds. And as we saw last week, one of the first things we have to do is we have to convert all weights into kilograms. So we're going to take that 99 pounds divided by 2.2, which gives us 45 kilograms for this patient. So we're dealing with a 45 kilogram patient. So now it's that 45 kilograms we're going to use to determine the safe dose based on the label on the bottle. And they're saying 10 to 12 milligrams per kilogram every 8 hours. Now in the first part, we're going to ignore the 8 hours, but we have to keep it. We're going to need that later. So we're starting out with our 45 kilograms. We're going to put that over 1. And then we're going to take that 10 to 12. We got to pick one of them. I'm going to take the 10 milligrams per kilogram. So in my conversion, I'm getting rid of kilograms and going to milligrams. So 10 milligrams per 1 kilogram. So the kilograms will cancel out, and I'm now in milligrams. So let's go ahead. 45 times 10 milligrams is 450 milligrams. And now we bring back the time frame. That is every 8 hours. This is, we use the 10, which is the smaller of the numbers. So this would be considered the minimum recommended dose. Well, if we want to find the maximum dose, we could do this calculation again. And in this problem, it's a single step, so it's not that hard to do. It's probably the route I would take. But we could also do a titration. A titration allows us to adjust the dosage based on minimum to maximum range, also on time variations. And what I'm actually going to do here first is I'm going to take this calculated minimum dose, and since that's over 8 hours, I'm going to convert it to a 6-hour dose to match it up with the doctor's orders. So we have 450 milligrams every 8 hours. And what we're going to do in our titration is we're going to multiply that by a titration fraction. And the bottom of the fraction is always the number that we use to calculate that first value. The 450 milligrams comes from the 8 hours. And we're converting it into 6 hours. So this becomes 450 times 6 divided by 8. Which is going to give us 337.5. So that is our minimum dose, 337.5 milligrams every 6 hours. We've just adjusted it to 6 hours to match the doctor's orders. To find the maximum dose now, we can also do a titration. We're going to take that 337.5. And that was found using the 10 milligrams per kilogram. We're going to titrate it to change it to 12, the maximum amount. So we take that 337.5 times 12 and divide it by 10. And we get 405. So that is telling us is 405 milligrams every 6 hours is the maximum dose for that size of a patient. So looking at the doctor's orders, which were 400 milligrams every 6 hours, that is within this acceptable range of 337 to 405. So that is a safe dose for that patient. Now again, this is a relatively simple problem because I gave you, everything in milligrams. But we might have doctor orders 80 milliliters of medication for a patient who weighs 132 pounds. And when the label says that this is concentrated at 25 milligrams in 4 milliliters, and that it should be given at, let me get the feel of this here. Oh, excuse me. See, the label says 4 milligrams to 5 milligrams per kilogram. That is per day. And this is 80 milliliters over 8 hours up here. So let's check to see the safe dosage here. So we've got the 80 milliliters over 8 hours is the doctor's orders. That's what we're going to be comparing back to. To find the safe dosage, the safe recommended dose, we're going to start out with our patient of 132 pounds. And again, since everything else is given in kilograms, we have to convert that into kilograms. And that conversion is just dividing by 2.2. So our patient is 60 kilograms. So we're going to start out this problem with 60 kilograms, put it over 1, and we're going to convert that into our dosage. Well, I'm going to start out with the 4 milligrams. We'll start with the bottom number again. So that's kilograms have to go on bottom so that they'll cancel. So that's 4 milligrams per 1 kilogram. However, in this case, we're not done at milligrams. Here we have to continue to go to milliliters. So I'll put milligrams on bottom, milliliters on top. And it says 25 milligrams in 4 milliliters. So now the milligrams are gone, and our only units here is milliliters, which is what we want. So we've got 60 times 4 times 4 is, 960, I believe, milliliters over 25. Oops, about 25. And we're going to get 38.4 milliliters. That is per day is the minimum dosage. But now the doctor's orders are given every 8 hours, so we need to convert that into every 8 hours. So 38.4. 1 day is 24 hours, so we're going to put 24 hours on bottom, and we're changing it to 8 hours. So it's times 8 divided by 24. We get 12.8. So 12.8 milliliters per 8 hours is the minimum recommended dose. To find the maximum, we use the 4. We now got to find out what it would have been for the 5. Again, we can use that titration. 12.8. We have the 4 on bottom. Oops, sorry, 4 on bottom. That's what we had used, and we're changing it to the 5. So 12.8 times 5 divided by 4. So you give us 16 is the maximum. So that is 16 milliliters over 8 hours is the maximum dose. So now looking back, the doctor ordered 80 milliliters over 8 hours, so that's nowhere near a safe dose. So we need to stop that dosage and ask for clarification. So that's kind of the highlights of these dosages based on weight. I want to do one more example, and then we're going to switch over to looking at body surface area. Body surface area is mostly for patients with skin, well, it is for skin conditions, a lot of times burn victims and other skin conditions, rashes, stuff like that. Medication can be doled out for body surface area. Let's do one more example here for our weight. So let's say our doctor orders 120 milliliters of medication every 8 hours. For a patient weighing 88 pounds. Our label says that there is 5 milligrams of medication in every 2 milliliters. So then we are looking at the recommended dosage here is, let's say it's 5 milligrams to 7 milligrams per kilogram every 6 hours. So again, the doctor's orders here are what we're going to kind of compare to when we're done, but we're going to start out calculating the dosage from scratch again from the patient's weight. So we have an 88-pound patient. What do we do to convert that to kilograms? Somebody be brave. Perfect. We divide by 2.2. Good. So that's going to give us 40 kilograms for our patient. So now we're going to take that 40 kilograms over 1. What's our next step to do with that 40 kilograms? Well, I'm going to pick, let's use the 7 this time instead of the 5. So what are we going to do with that 7 milligrams per kilogram? Which one has to go on bottom in our conversion? The 7 milligrams or the 1 kilogram? The 1 kilogram. Because it has to cancel out with this kilogram here. So our 7 milligrams will go on top. And the kilogram's gone. But that's not our last step this time. We have another step. What goes into this next step? We're converting from milligrams into what? Milliliters, good. So we got milligrams here. We're getting rid of milligrams, so they go on bottom, going to milliliters. So 5 milligrams equals 2 milliliters. So the milligrams are gone. So we're going to have milliliters. So 40 times 7 times 2 divided by 5 is going to give us, what, 5,612, I believe, milliliters. I'm going to double check that. Yes, it is 112 milliliters. And now we do have to come back up here and grab this time frame. That is per 6 hours. That is, we use the larger number, so that is the maximum. Now we have to change that because the doctor's orders are every 8 hours. So we're going to take our 112 here. And in our fraction, what number is going to go on bottom? How many hours is it currently over? 6 hours. 112 milliliters over 6 hours. And we want to change it to how many hours? The doctor's orders are for 8 hours. So we're going to take that 112 times 8 divided by 6 to get 149.33. So that's telling us 149 and 1/3 basically, 0.33 milliliters every 8 hours is the maximum dose. To find the minimum dose, we're going to take that 149.33 and now we are going with this here, the 5 and the 7. We found the maximum dose using the 7, so the 7 is going to go on bottom. We'll put the 5 on top. So our 149.33333 times 5 divided by 7 is 106.67. So 106.67 milliliters over 8 hours is our minimum recommended dose. If the doctor's orders of 120 fall in that range. Now here's that titration is very important in keeping track of that time. Because in our original calculation here, we came up with only 112 milliliters. So that was as the maximum, which would make it look like that 120 is too much. But we have to realize that this is over 6 hours. So we have to make sure we do that titration as we did here to adjust that to 8 hours. All right, so now we're going to talk about body surface area. And most of the time, rather than writing it out, you're going to see me just say BSA. Now, as I mentioned, body surface area is used for finding medications for burn victims, patients with skin conditions, severe rashes, eczema, stuff like that. It's really a straightforward calculation. The formula method is probably the best method of doing it, which is an estimate, again, based on assuming your standard proportions of a human being. You know, if somebody had missing limbs or something like that, this formula would obviously be incorrect. But if we start out with standard measure, in other words, our weight is in pounds and our height is in inches. The body surface area in meters squared is found by taking the height in inches times the weight in pounds and dividing by 3,131. So if we have a patient who is 68 inches tall and weighs 175 pounds, this formula will become the square root of 68 times 175 divided by 3,131. So second square root 68 times 175 divided by 3,131. So 1.949 and 1.95. We generally round to 2 decimal places for body surface area. So 1.95 meters squared. If we have metric measurement, so in metric measurement, our height is going to be in centimeters, and our weight is kilograms. And as we mentioned before, kilograms is technically mass, but we're using it for weight. Our body surface area, still in meters squared, is going to be the square root of the height times the weight divided by 3,600. So here, if we have a patient who's 182 centimeters tall and has a weight of 80 kilograms, their body surface area will be the height of 182 times the weight of 80 over 3,600. So again, second square root 182 times 80 divided by 3,600. 2.01 we get. That's meters squared of body surface area. So the estimated body surface area of that patient is 2.01 square meters. So the formula isn't so difficult. It's pretty quick and pretty simple to plug in. The only tough part of it is if you don't have a calculator, doing the square root can be kind of intimidating. So there is something that they use called a nomogram. Now a nomogram is, I just spelled it wrong, it should be N-O. A nomogram is actually a graphic display for figuring things out. It can be used for BMI, body mass index, as well as other things. And what it involves is having two values and using them to find a given value. So you might have value A over here and value B over here. You find the value for the A variable, the value for the B variable, you connect them with a line, and then you look at, okay, where does that cross this X variable? What value does that give you? So you're lining things up to see where they cross. And let's take a look. Now, if I go back to these examples here, 182 centimeters and 80 kilograms, I don't believe that'll even appear on this nomogram. Actually, it does barely appear. 80 kilograms is the top of the weight on this nomogram. Let me show you what I mean here. The weight is displayed over here on this column. So this axis all the way down here is displaying the weight. The right side is kilograms, the left side is pounds. So a side effect of this is you can actually use this as a rough way of estimating the conversion between pounds and kilograms if you want to. You can see here 80 kilograms is just under 180 pounds. So anyway, I'm going to put a dot there at my 80 kilograms. We're going to be lining that up with the height on the other side. Now you see 80 kilograms, 180 pounds is not that large. Anything over 180 pounds, we cannot use this nomogram for. That patient was 182 centimeters in height. So if we're on the height, we're going to find 182. Now here's one of the weaknesses. If it was 180, it'd be really easy to find. Those exact numbers in between are a little bit more difficult. So here's 180 and 190 over here. Here's the height, centimeters on the left, inches on the right. There it looks like there's 5 gaps, so each is worth 2 pounds. So this is 182 right there. That's where that red dot is. So now we have to connect them. So I'm just going to, since I'm using a Word document here, I'm going to use the draw tools in Word to connect them. So there's my line. I'm going to make that a little darker quick. And make it red so we can see it better. So that line cuts across there. And we can see I got a little bit high on this end here. I can try to pull it down. The grid lines are going to mess me up a little bit. But anyway, you can see here in the middle, this is the body surface area here in meters squared. And you see it comes across here just above the 2.0. This one's labeled 1.8, so this one must be 1.9. So to me that looks like it'd be like a 2.1 or a 2.2. And our calculation for that one was 2.01. So here the nomogram is giving us a number a little bit larger than what the formula did. Well, let's take a look. Let's do some smaller numbers here. Let's say we have a patient that is 61 inches tall and weighs 128 pounds. So we're going to find the height over here on the left side, 61 inches. You're right there. Between 60 and 65, there's 5 gaps. It looks like each gap is 1 inch. And we said 128 pounds? Yes. So 128 pounds over here. Here's 120, 130. 128 is going to be somewhere here between 125 and 130. About there looks pretty close. So here in the middle, we're between 1.6 and 1.65. I'd say that's 1.62 maybe. Again, you're kind of estimating in between the lines there. So let's go back here and calculate. We had 1.62 is our estimate from the nomogram. Let's calculate with a formula. So we have 61 inches times 128 pounds. What number goes on the bottom of this formula? 3131 or 3600? Because we're in standard measurement, inches and pounds, we have to use the 3131. So we'll find that second square root. 61 times 128. Notice I don't have to use any parentheses or anything inside my square root because the order of operations will do this correctly. Just height times weight divided by the 3131. 1.58 it looks like is what I'm getting here. Meters squared. So once again, the nomogram is a little bit larger than what the formula gives us. And it usually is pretty consistent that way, that the nomogram will be a few hundredths of a square meter larger than what the formula does. So here it's like 4/100ths of a square meter larger. So now if we look back at this nomogram, there is this extra little piece in here. This box here is actually a completely separate chart. These 3 columns go together. Those 3 columns actually make up the nomogram. But because of the way that they needed to be set up to line up so we could run this line across, the BSA was going to have to be a lot closer to the weight. And you had to get the weight and the height far enough apart so we get the scale spread out to where you could actually use it. They ended up with this big gap in the table right here. Well, to fill up that gap, a lot of charts do this. Not all of them do. Some of them will leave it blank. But to fill up that gap, a lot of them put this extra table in here. What this extra table is body surface area for children of normal height for their weight. In other words, their height and weight proportional. They're on the normal charts for their height, given their weight, or for their weight given their height, I should say. And in that case, if we have that normal, their height and weight proportional, we can look up just based on their weight in pounds here. We can find their body surface area. I don't know why they used pounds here instead of kilograms. They seem to be using kilograms for everything else. But for this chart, they did use pounds. So if I have a child who is normal weight for their height, and weighs 48 pounds. Their body surface area can be found on this chart. This chart goes up to 90 pounds here for this one. 48 is going to be in here. I'll move this out of the way. Here's 40 and here's 50, and there are 5 gaps between them. So each gap, 10 divided by 5 is 2 pounds. So this child weighing 48 pounds, this would be 40, 42, 44, 46, 48. Right there is where the 48 pounds is. This is 0.8 and 0.9 square meters. Again, there's 5 gaps between there, so that's 0.02 per gap. So this is 0.82, 0.84, 0.86 would be that one, so it's between 0.84 and 0.86. So I'm going to say it's 0.85 square meters. It's between 0.84 and 0.86. Now, if we look closely, it's actually showing slightly closer to the 0.84. So we might could have said 0.845 or something like that if we wanted to. I always caution between being too precise with your estimates. If we were doing like a formal tech math class for measurement, we actually wouldn't allow you to estimate between lines at all. You just have to go to whichever line is closest. But for our purposes, we will estimate between. And we'll say that's 0.885 or whatever. You might want to argue it might be 0.82, 0.83 or whatever you want to call it. So let's go back and find this one in our formula. This can be also used, by the way, to determine whether a child is normal height for their weight. We got 0.85 square meters here. And let's say that this child is 48 pounds, and what do I want to put in for a height? Let's say that they are 42 inches tall. So their body surface area is going to be the square root of their height, 42 inches, times their weight of 48 pounds, over, again, it'd be 31. So second square root, 42 times 48, divided by 3,131. We get 0.802. So 0.80 square meters. So 42 inches might be a little short for this patient. Let's actually look it up on the regular nomogram here. So 48 pounds and 42 inches. Over here on the right side, 48 pounds. It's going to be all the way down here. So just under the 50, somewhere in there is going to be 48. Probably about like that. That's between 45 and 50. And we said 42 inches. So inches, right there's 42. And that is saying 0.82 about. So that nomogram is actually giving us a number between the formula and the estimate. But it is closer to our formula than the other table is. One of the ironies of this nomogram is the weight only goes up to 80 kilograms or 180 pounds, but the height goes up to 90 inches. I'm not going to be running into too many patients that are 8 or 7'6", hopefully. So now let's take a look at some dosages based on this. So let's say our label says to give 4 milligrams per square meter per day, and that it is concentrated here in, let's say it is in 8 milligrams in 5 milliliters. And we have a patient who is 74 inches tall and 260 pounds. So the first thing we need to do is find the body surface area for this patient. So it's going to be the square root of 74 times 260 over 3,131. So second square root 74 times 260 divided by 3131. So we get 2.48, it looks like, square meters. So now instead of starting out with a weight in kilograms, we're starting out with a body surface area in square meters. And we're going to do the conversion from that, 4 milligrams per square meter. So square meters go on bottom, milligrams on top. 4 milligrams per 1 square meter. The square meters cancel out. We now have milligrams. But we do have to go to the next step here. This is stating 8 milligrams per 5 milliliters. So milligrams on bottom, 8 milligrams to 5 milliliters. Milligrams disappear. So 2.48 times 4 times 5 is 49.6, I believe, milliliters over 8. Which gives us 6.2 milliliters. Now we do have to go back and get our time frame that is per day. So that patient should receive 6.2 milliliters per day. So for those of you in Boston, that's a good flavor of what we did last week while you guys are on spring break. Those videos are out there on Blackboard. Remember, you go into Blackboard. Oops, I haven't logged in yet. Let me log in here quick. If you go into Blackboard for this course, you'll just click on course information, and those recordings should be down at the bottom of the page, and they are listed by date for you. So it's the 317, 327, 329 videos that you need. Looks like I still have to post the 331 video, so I'll get that done for you in the next couple hours. So homework, pages dealing with body surface area. We're going to look at page 196 through 197. 1 through 19, the odds. If you haven't done it yet, again, go back and do page 189 or 188 through 190, 1 through 21, the odds. Dealing with those titrations and safe dosages as well. On Wednesday, we're going to do more examples of these dosage calculations to make sure we've got all the different possibilities down. Do a little bit of review for some of the stuff we did, since it's kind of been spread out, being split up with spring breaks here. You do a little bit of review, and then this Friday will be our unit test. So make sure we're prepared for that. Okay, so that is it for our new material. So you guys have a great day, and we'll see you on Wednesday.